Hello dear students, welcome to the course of Engineering Thermodynamics. Myself Mihir Mistry, Assistant Professor from Mechanical Department of LJ Institute of Engineering and Technology. So today we are going to continue our session on vapor power cycles, and in particular we are going to discuss about Rankine cycle example. So let us start the second example. So let us read the data first given on the screen. A steam turbine of a power plant operating on ideal Rankine cycle receives steam at 20 bar and 300 degrees Celsius. Now you can see here that the steam is supplied at the inlet of the turbine. Here steam turbine receives, that means at the inlet of the turbine the condition of the steam is given, that is 20 bar and 300 degrees Celsius. Clear? Next, at the rate of 3 kg per second, that is mass flow rate given 3 kg per second, students. Keep that thing in your mind. It exhausts at 0.1 bar. Okay, so exhaust, that means at the outlet of the turbine, the pressure of the steam will be 0.1 bar. Determine the following. What are the following? Net power output and Rankine cycle efficiency. Okay, so we will first write down the given data. So as you can see from the first line, turbine. So now the inlet of the turbine, I will denote inlet of the turbine as 1 point. So right now I have pressure at 1 point and temperature at 1 point. So my P1 is 20 bar and my T1 is 300 degrees Celsius. So P1 20 bar, that will be equivalent to 2000 kilopascal, right? That is the standard conversion. Remember the conversion, 1 bar is equal to 10⁵ Pascal. Okay. Now further, temperature is given, that is T1 is 300 degrees Celsius. So convert it into Kelvin, that will be 573 Kelvin. Right? Further, mass flow rate m dot is given as 3 kg per second, and the exhaust pressure is 0.1 bar. Now exhaust pressure, that means at the outlet of the turbine. So if outlet of the turbine is denoted as point number 2, then T2 is given as 0.1 bar. Clear everyone? So 0.1 bar is given, that will be equivalent to 10 kilopascal. Clear? So now further we are supposed to find out net power output. Now mark the words, work output and power output, that is a difference. Work output, if it is asked, then your unit will be kilojoule per kg, and if power output is asked, then your unit will be kilowatt. Okay, so here power output is asked, that means you have to multiply the work with mass flow rate, that will give you the power output, right? So also you can say W dot, that will be the power output. Rate of work, that is power. Okay, so that is why W dot. Now Rankine cycle efficiency, that means eta, that is also we are supposed to find out here. Okay, so first approach is what, students? First approach is you should know or you should be aware about the equations that you are supposed to find out. Okay, so you are aware that work done, net rate of work done is equal to what? Rate of work done is equal to mass flow rate into net work. Okay, so first of all, that is important equation, and net work is equal to what? Turbine work minus pump work. Okay, now turbine work, so turbine work is equal to what? So turbine is in between 1 and 2 point, right? And pump is in between 3 and 4 point. We will see that in and understand it in diagram, TS diagram. But as of now, net work is what? Difference between turbine work and pump work. Clear? Now further, next thing is efficiency. Efficiency is equal to what? Net work divided by heat supply, right? And that is the equation of efficiency. Okay, now we will plot the diagram, that is TS diagram. But before plotting the diagram of TS, you should know the condition of the steam at the inlet of the turbine. I am repeating again. Before drawing the TS diagram, you should know the condition of the steam at the inlet of the turbine. Okay, so here the condition is not written. If you observe the example number 1 that we have already discussed, that in that example the condition was written with the word saturated. Here nothing is written like that. Okay, so here the pressure and temperature is given, that is 20 bar and 300 degrees Celsius. So what you will do, you will open the steam table, and which steam table you will open? Obviously pressure base. So in the bracket it will be written pressure table. So open the steam table and identify 20 bar pressure in that steam table. The steam table which I am referring is using kilopascal as the unit of pressure. So that is why I have converted bar into kilopascal, right? So now further what we will do, at 20 kilopascal I will identify the saturation temperature. Note down the saturation temperature. So as you can see on the screen also I have written that saturation temperature is 212.38 degrees Celsius at 20 bar or 2000 kilopascal. Clear? So now just think logically that at the inlet of the turbine the temperature of the steam is 300 degrees Celsius, and if you are having pressure of 20 bar, then saturation temperature is 212.38 degrees Celsius. Now what is the significance of saturation temperature? Significance of saturation temperature is if you have 20 bar pressure, then your water will start boiling at 212.38 degrees Celsius. So, but obviously at 300 degrees Celsius, your water will be already converted into steam. Okay, so that is why I can say that at 300 degrees Celsius, the steam will be known as superheated steam. Clear? So what is the condition for identifying the superheated steam? The condition is if the given temperature at the inlet of the turbine is higher than the saturation temperature at the same pressure at the inlet of the turbine, then your steam will be superheated steam. Clear, students? So here you can see saturation temperature is less than T1, or you can say T1 is greater than Tsat. So that is why steam is superheated at point number 1. So if the steam is superheated at point number 1, then you can plot the TS diagram as shown in the screen. Okay, so as you can see in the screen, one point will be in the vapor region, okay, outside the dome. Okay, so that is the significance of identifying the condition of steam at point number 1. Clear? Now you know that from 1 to 2 you will have reversible adiabatic or isentropic process, so straight vertical line. Obviously 2 point will be most of the time it be in wet region. Then 2 to 3 point will be obviously all times, majority of the time 3 point will be saturated liquid line, and 4 point will be on pure liquid line, and 4 to 1 back you will go, then it will be the heat addition process. Okay, so that is the TS diagram you will draw. Okay, so first if you refer any Rankine cycle example or any vapor cycle example, first identify the condition of the steam, then plot the diagram. Okay, so it will be much more clear. Okay, so now I will write down the equation for turbine work and pump work. So what is the equation for turbine work and pump work, students? So now you can see and you can appreciate that turbine will be located between 1 and 2 points. So turbine work will be equal to H1 minus H2. And same way pump will be located between 3 and 4 points. So pump work will be equal to H4 minus H3. Clear? Now further you will put all this equation in efficiency equation and a rate of work transfer equation, so you will get your answer. So ultimately the goal is to identify 4 enthalpy. Then you can manage all the answers that are asked in the question. Okay, so let us find out all the 4 enthalpies. So very first is H1. So now you should know that at point number 1 the condition of the steam is superheated steam. So if superheated steam is given, then what is the equation of superheated steam? You know, right? We have already discussed. So superheated steam H1 is equal to Hg plus Cps into T superheated minus T saturated, right? That is the equation for superheated steam. Okay, enthalpy of superheated steam. If you don't know this, how this has occurred, then you can refer the steam formation diagram lecture. Okay, so that will be equivalent to H1 is equal to Hg plus Cps into T superheated minus T saturated. Now observe over here, students, in this equation, we have to find out Hg, we should have Cps, we should have T superheated, we should have T saturated. Now let us find out which values we already have. Okay, so first of all Hg. So Hg, do we have Hg? So yes, Hg is, we do have Hg. But for finding out Hg from steam table you will require pressure. So which pressure you will take? So obviously Hg is corresponding to point number 1. So corresponding to point number 1, which pressure is given? So you know and you can appreciate from the diagram of TS that from 4 to 1 you have constant pressure, that is equivalent to 20 bar. So if 20 bar is your pressure, That means at 20 bar in steam table, you can identify the value of Hg, right? That will be your Hg. Okay, further CPS I have already told you many times, if it is not given in the data, then you can take 2.1 kilojoule per kg Kelvin. That is the specific heat of superheated steam at constant pressure. Clear? Further, T superheated is already given, that is 300 degrees Celsius or 573 Kelvin, minus T saturated. T saturated is 212.38 degrees Celsius. You convert it into Kelvin, it will be 485.38 Kelvin. Clear everyone? So you substitute all the values, then you will have the final value of H1 as 2982.302 kilojoule per kg. Clear? Easy to understand, nothing big. Okay, now we will move forward for H2. Now H2, point 2 is in wet region. Right, so point 2 is in wet region. Now you know, if you have seen the video of example 1, now you know what you are supposed to do for finding out H2. Obviously, point 2 is in wet region, so enthalpy of wet steam is equal to what? H2 is equal to HF2 plus X2 HFG2, right? So that is the equation for enthalpy of wet steam. Now here HF2, right, and HFG2, right, and X2. You should have the value of HF2, X2 and HFG2. Now remember students, point 2 is in wet region, and what is the pressure corresponding to point 2? Now you can appreciate that pressure corresponding to point 2 is 0.1 bar. So what you will do, you can identify the value of HF and HFG at pressure 0.1 bar from the steam table, right? Clear everyone? Okay, but the question is, we don't have X2. Okay, we don't have X2. So first we will have to manage to find out X2, because we can manage to find out HF and HFG at 0.1 bar from steam table easily. But X2 we should have first. Okay, then we will be able to solve the problem for H2. Okay, so let us find X2. For finding out X2, we will find the entropy of point number 2. Now you know that entropy of wet steam can be written as S2 is equal to SF2 plus X2 SFG2. Clear everyone? S2 is equal to SF2 plus X2 SFG2. Mark my words, this is very important. Majority of the students are making mistake at this point. Now here SF2 and SFG2, that means SF and SFG, at which pressure you will take? So obviously at point number 2, and corresponding to point number 2, the pressure which you will refer is 0.1 bar. So you will take SF and SFG at 0.1 bar from steam table. Clear students, everyone? Okay. Now still we are supposed to find out, our aim is to find out X2. But if in this equation, if we want to find out X2, then we should also know the value of S2. Right? So first I have to find out S2. Now you can appreciate over here, process 1 to 2 is drawn as straight vertical line. And what is the significance of straight vertical line? The significance is the entropy of point number 1 and point number 2 will be same. That is the S1 is equal to S2. Now that means I can take S2 is equal to S1. Okay. Now S1. So point number 1 is superheated steam. Right? So what I will do? I will have to find out the entropy of superheated steam. Now the equation for finding out the entropy of the superheated steam is this one. S1 is equal to Sg plus Cps ln T superheated divided by T saturated. Okay, so that is, remember students, this is the equation for entropy of superheated steam. Okay, you might be encountering it with first time, so keep this thing in your mind. Okay, so S1 is equal to Sg plus Cps ln T superheated divided by T saturated. That is the entropy of superheated steam. Okay, so in this equation, Sg, let us find out Sg. So at which pressure you will take Sg? So obviously Sg will be taken at point number 1, and point corresponding to point number 1, the pressure given is 20 bar. So from steam table at 20 bar, you will find out the value of Sg. Cps is already given, right? That is 2.1. T superheated is 300 degrees Celsius and T saturated is 212.38 degrees Celsius. Remember student, in LNT superheated by T saturated, always take temperature in Kelvin. Don't make mistake of taking the temperature in degrees Celsius. Clear? Okay. Now that means what? That means here for the equation of S1 or entropy of superheated steam, we have all the values available with us, that is Sg, Cps, T superheated and T saturated. So we can easily manage to find out S1. So if we have S1, then S1 equal to S2. We are going in reverse order. Observe the right hand section of the screen. So S1 is equal to S2. If we have S2, then we can find out X2. If we have X2, then we can find out H2. Right? So we will do this calculation in the next slide. So now let us do that. So at 20 bar, I will first identify Sg. So from steam table, I can see that the Sg is 6.3390 at 20 bar or 2000 kilopascal. Right? So I will substitute the value in S1 is equal to Sg plus Cps LNT superheated by T saturation equation. So if I will substitute the value, then the final answer for S1 will be 6.6875, and here you can appreciate, observe the TS diagram, S1 and S2 both values will be same. Okay, so that means my S2 will be also equal to 6.6875. Okay, now here S2, what is the equation for S2? 2 point is in wet region, so equation for S2 is equal to SF2 plus X2 SFG2. Okay, so here at 1.1 bar, you should know the value of SF and SFG, because now we want to find out X2, right, using entropy of point number 2. So we already have S2, we have to find out SF and SFG. But SF and SFG at point number 2. So for that, which pressure you will take? You will take 0.1 bar. Remember student, don't make mistake of taking 20 bar pressure. Okay, because we are dealing with point number 2. So corresponding to point number 2, the pressure given is 0.1 bar. That is why at 0.1 bar pressure, you will take SF and SFG from the steam table and substitute in this equation. So in this equation, we have S2, SF2, SFG2. So you can find out X2 as 0.805. Clear everyone? Okay, now we have X2. So now we can easily find out H2. So for finding out H2 is equal to what? HF2 plus X2 HFG2. So in this equation also, HF and HFG both can be found out at which pressure? At 0.1 bar. So how at 0.1 bar? Because observe in TS diagram that your point number 2 is located for process 2 to 3, and for whole 2 to 3 process, your pressure will remain constant as 0.1 bar. Clear everyone? So at 0.1 bar, identify HF and HFG from the steam table. X2 you already have, substitute the value, you can find out the value of H2 as 2117.45 kilojoule per kg. Okay, now further for H3. So point number 3 is in saturated liquid line. So if it is on saturated liquid line, then the enthalpy of saturated liquid is equal to HF. But HF at which pressure? Now you know that corresponding to point number 3, the pressure is 0.1 bar. So you will take HF at 0.1 bar. So that is 191.81 kilojoule per kg. That will be H3. Clear? Now H4. So for H4, we will use the equation of pump work, because 3 to 4 is the process in the pump. Okay, so for pump work, you know that H4 minus H3 is equal to VF3 P4 minus P3. How this equation is derived, sir? Observe or recall the lecture of Rankine cycle. Okay, in that I have explained how this equation can be derived. Okay, H4 we are supposed to find out, H3 we already have, VF3. Okay, so VF3. So now here VF3 means what? Specific volume of saturated liquid. Okay, specific volume of saturated liquid. At which pressure? So corresponding to point number 3, the pressure given is 0.1 bar. So at 0.1 bar, whatever the value of VF is given in steam table, you will take that value. Okay, so VF3 is nothing but Vf at 0.1 bar from the steam table. Okay, students, so that is equivalent to 0.001010 meter cube per kg. Sir, what is the significance of this specific volume? Simple, student. If you will take 1 kilogram of water at 0.1 bar pressure, then that 1 kg of water will require the space of 0.001010 meter cube. Clear? Okay. Now let us move forward. So we have VF3. Now P4 and P3. Now just pause this video for a second and tell me what is P4 and P3. Simple. See, P4 is equivalent to P1 and P3 is equivalent to P2 because 4 to 1 and 2 to 3 both are constant pressure process, right? So P4 is equivalent to P1, that is equivalent to 20 bar, and P3 is equivalent to P2, that is equivalent to 0.1 bar. So you will substitute that value. But here remember, students, your specific volume is in meter cube per kg, that is pure SI unit. So you have to convert all enthalpy and pressure units into SI unit. What I am trying to say is, observe on the screen. Here for H4, we are going to find out for H3 the value is 1.81 kilojoule per kg. So I have converted from kilojoule to joule. So multiply it by 10 raised to power 3. That is what you are supposed to do here. Okay, that is equivalent to VF3. What is the value of VF3? 0.001010 into P4 minus P3. What is the value of P4 and P3? 20 minus 0.1. Now 20 and 0.1 is in bar. So you have to convert it into Pascal because SI unit of pressure is Pascal or Newton per meter square. So convert bar into Pascal. So you have to multiply it by 10 raised to power 5. That is why I have multiplied it by 10 raised to power 5. Clear? Now if you will do so, do this calculation, you can find out H4 as 193.819 kilojoule per kg. Very simple, right? Now further we have all the values of H1, H2, H3 and H4. Substitute this value in the equation of rate of work done, then you can have the power because m dot is given, H1, H2, H3, H4 we have already found out. So power produced will be equivalent to 2588.529 kilowatt. Okay, students, and same way efficiency of the Rankine cycle can be found out using the enthalpy as 0.3094 or 30.94%. Okay, now here you can observe and appreciate that the pump work, see at H3 you have the enthalpy of 191.81 and at H4 you have the enthalpy of 193.819. Okay, so there is very small pump work. So many times in academic numericals it will be asked to neglect the pump work. The reason is this: you have only around approximately 2 and 2.5 kg per kilojoule per kg of pump work. So that is small or negligible compared to the turbine work. That is why majority of the time in numericals it is asked to neglect the pump work. Okay, if it is asked to neglect, then you have to neglect it. Otherwise, you should take the pump work. Okay, now that is all for this example. Okay, thank you.